Good evening, everyone. Welcome to today's session, live interaction session for the course Computational Mathematics with SageMath conducted by NPTEL. As is the custom every week, we'll be going through a few problems based on the concepts that have been taught for that particular week, and we'll go through them step by step and try to understand better the concepts that have been taught. So, So the first thing that we learned in this week was about integrals, specifically indefinite as well as definite integrals. How do we evaluate them? So the first example is on the same lines where it asks us about evaluating indefinite integrals. So the first function that we have been given, the first function that we have been given is of the form. Yeah, this is better. Minus 4 upon root of 1 minus x squared dx. So we begin first by specifying variable x, and then we define a function f of x, which is minus 4 by square root of 1 minus x squared. And if I do show of it, I get something like this. Right? If I want to see how this function would look like, then I could use the plot function. So say plot f, and we have to restrict x between minus 1 and 1. That this is quite evident once you look at the denominator, which has 1 over 1 minus x, 1 minus x square in it. So this is how f of x looks like. And to integrate, we'll use the f dot integral method. So function dot integral method. If you look at the help on the same, we see that it requires it's a method on the expression instance. So you have expression dot integral, and whatever series of or a list of arguments that you want to provide, you can provide that. It works using symbolic integration, and it can also help us evaluate definite integrals. So if I integrate f of x, I'll get a function capital F of x. If I do show, what do I get? I get a function of this minus 4 arc sine of x. So if I have to plot f, if I just put this, I say this is my integral. So indefinite integral. The okay, so this is how indefinite integrals can be evaluated. Second, another function, say something of the form of 2 of twice of x into cos of 2x. If you want to integrate that, we'll again do a g dot integral with respect to the variable x. And since we are not providing any limits to x, this will calculate the indefinite integral. So this is how the indefinite integral looks like. If I want to plot, say both the functions together, I can do, so p1 is equal to plot of g, and p2 is equal to plot of capital G, and then do p1 plus p2. So I should perhaps put color equals green. Right, so this becomes my indefinite integral. A third, I have like a couple of other functions also here. A third function is, say, something of the form 2x raised to 5 plus x square plus x plus 1. If I do show, this is how the function looks like. Again, I'll integrate it. It's a product of, sorry, it's a fraction of two polynomials, and from that we can get an integral of the form. Another function could be something like cos of x whole square and sine of x whole raised to 5. So we could integrate that also. So this expression dot integral gives us indefinite integral, Now we'll evaluate a few definite integrals. Suppose that we are given the expression, we want to evaluate tan of x square between 0 to 1, integral of tan of x square between 0 to 1. Again, if I look through the help, it's showing that I can do function dot integral and then variable and its limits. So using this command, I'll be integrating the function f, and this should this will take a, you can see that this has not been solved. So to get the numerical value, we do dot of n to the expression. Okay. There are a couple more examples in the same line that we could do. Say, suppose square root of 2x cube plus 1. And if we want to integrate it between 0 to 2, we get something of the form of gamma function, which we can later evaluate into its specific numerical value. Another function here is of the form 3x upon root of 3x minus 1, and this is being integrated from 1 to 4. Right, so x cannot be less than 1 by 3 because the denominator will become 0, or the denominator will be no longer positive. Another expression. So straightforward. If the function is integrable by the symbolic integration calculator, f dot integral will get us the integrated value of expression of the indefinite integral, to which we can later apply bounds to evaluate the definite integral. Okay, so I think this is straightforward in itself. Next example we have is about the concept of Riemann's sum, specifically left and right Riemann sum, and uh, how they help us evaluate integrate how they help us to calculate the integration of different expressions. So we have been asked to calculate left and right Riemann sum for the integral 0 to pi sine of x square dx, and we have been asked to do it with different types of different number of bins. So let us first begin by looking by specifying the variable, defining the function, as well as seeing a plot of the function over the range with which we want to integrate. So sine of x square, not sine of x whole square, would look something like this, and it will keep on shrinking. So if I have to say, it's no longer periodic. It's periodic sine. It's periodic only if you plot it versus x square. So we are plotting f of x versus x. This is how the function looks like. Next, we look at the left Riemann sum. To define it, we'll be first specifying our bounds, which are a and b. Number of bins. This r is a factor that basically differentiates between whether we are at the left end of the bin or the right end of the bin or midpoint of the bin. We define delta as the difference between width of each bin, that is nothing but the limits divided by total number of difference between limits divided by total number of bins. And once this is there, what we do is basically we look for all the number of bins, and for each bin we'll be adding our point x comma y into the list itself. So that would get us, say, the list of points. Next, another thing is we want to evaluate the integration. To do that, we'll be calculating y at a particular point. So y at f of x k plus delta, and then adding it to, say, the s value, which will hold our sum. So if I do this, I'll run this code. So we have already seen this in class. Professor also shared this uh, notebook, so you could go through the code in detail if you want, or if you have any doubts right now, you could also stop me here. So basically what we are doing is we are plotting f of x Then in the plot we are adding different bins made of different bins, and you can see that in the left dimension, whatever value y of x gets, that becomes the height of our bin. We could uh, we could specifically define functions for left and right dimension, which take a function as an input, or left and right limits for the definite integral, and the number of bins we wish to use for our Riemann sum. So from this we can calculate what is our bin width, and which is delta, and then you multiply bin width with the sum of an array whose all elements are basically y of x or y of x plus delta, depending on whether it's a left Riemann sum or a right Riemann sum. So I have defined these two simple functions here, and then I'm creating a table wherein I'm giving an array for the number of bins. They vary from 10 to 1000, and you can see that for each n in this array, I'm calculating the left Riemann sum, the right Riemann sum, and basically uh, appending this to a list called as rows. The first element of the rows contains my headers for the table, which are number of intervals, left Riemann sum, and right Riemann sum. If I run this code, it will take a moment, and then I'll ask it to show me the table. So I'm doing two things. First is I'm printing the table, and the second is I'm doing a calculation for the integral using analytical method. So that gives me a value of 0.7726. My left and right Riemann sums give after 1000 wins values of 0.7733 and 0.7719. You can see that it's becoming more and more accurate as we go from as we increase the number of intervals. So straightforward. Uh, so a straightforward example of left and right Riemann sum. The next example that we have is we want to calculate the average value of a function, which is x over 1 plus x square whole square on a given interval. The interval is between 0 and 2. From this, we wish to verify the mean value theorem and also plot f of x and the comparing f of x with the mean value. So again, we begin by the same steps. First, start by initialization, which includes initializing variable x, our limits a and b, and my function f of x. So my function form is correct. Next, I'll create a plot of f between a and b. So this is how my f of x looks like. To calculate the for the mean value theorem, we wish to calculate the average value this function takes. So that is nothing but 1 over interval width, which is b minus a, into into integral of f over the variable x with limits a and b. So once I do that, I'll also ask it to evaluate the answer in a numerical value. So which gives me that the average value of this function over this interval is 0.2. So it's so there are, you can already see that there are points where this mean value will intersect. If I do a plot for the function as well as a line for the average value of x, y is equal to average value of f of x between the intervals a and b, this is what I see. So these are my this is my function as well as the mean value. From mean value theorem, we know that this will cut the function at least at some point. So this is what we see. There are 2 points where f of x equals mean value. If I wish to say solve for this, I could do say solve f of x equaling f average dot n and ask it to calculate. So if I do this, f average. I'll get values such as this. So if I do s of 1 of x, and if I do, so there are some non-negative, sorry, 0. So there are two conjugate solutions as well, and we are interested in the real solutions. Those should be 0.219, so somewhere here, and another solution would be somewhere around 1.2. Yeah. So these are our 2 points, right? So this is what we see here. So the function indeed intersects at the mean value for the interval. Okay. Uh, so now the next example, we have a we have been given, say, a hypothetical rod with certain length, and we have been told that it has a density which is a function of position. We are asked to calculate average density of the rod. So again, the same process. You begin by initializing the variable, the limits of your integral or the limits of your function, and your function itself f of x. If I plot this function, it looks something like this. And now I'll calculate the average value of this function over the interval. The average density, it says it turns out to be 4. And again, it's straightforward. It's 1 over integral, 1 over interval into integration of f of x between limits a and b. And if I plot the function as well as the mean value, it intersects at one point. If we wish to see what point it is, we could simply do this again. So that would give us, sorry, I have to see this. So that gives us exactly 1 point. X is equal to 4. So if I do S0 X, X1, and if I now plot f of x equals X1, in like a perfect match. Okay, so this also, uh, okay, so now we know uh, now we have solved this problem also. The next problem that we want to see is evaluating integrals, but now the limits have been pushed to infinity. So to do those will be again same process, define the variable, define the function, calculate the integral, again by doing f dot integral from the range minus infinity to infinity. So the integral of 1 over x square dx from minus infinity to infinity is turns out to be y. Next, we have been asked to calculate e raised to minus x square, x raised to 2n minus 1 from 0 to infinity. So if again x needs to be positive, because otherwise e raised to minus x square will just blow up to infinity. So you can see that as x increases, e raised to minus x square will quickly drop to 0. X raised to 2n plus 1 will keep on increasing. So somewhere after a point, your function will become a small value. If I again do the same thing, define g of x as e raised to minus x square into x to 2n minus 1. And now I use the integral command. So I get half of gamma by n as my answer. Okay. Uh, it's important here that n is positive. 2n minus 1, x raised to 2n minus 1 then becomes an increasing function, but it doesn't increase as fast as e raised to minus x square decreases. So if I wanted to look at, say, only one specific plot, I could say 2 raised 1 minus 1, and if I do plot of g, this is how function would look like. If I say do for n equals 3, function seems to be becoming flatter. I have to restrict it to x 0, say 100. So it will peak at some point and then drop. If I say push this to even say 50, again it will peak somewhere and drop. Okay, so right, so this is what we get. Okay. Next function that we have is a function of the form 1 over f of x equals 1 over square root of 2 pi s into e raised to minus of x minus m whole square upon s square. And sorry, and we have been asked to plot f of x for some given value m and s. You can see that this is basically a Gaussian function with the mean m and variance s. So this is how it looks like. If I show f of x, I think I need to do this to pi of s. And if I know plot g of x, that's how the Gaussian looks like. If I do an integral from minus infinity to infinity. So this is basically a Gaussian with uh, m equaling 5 and s equals 2. If I just push it, the next example that we have is we want to plot a curve of the form y of x equals 1 plus x square whole raised to 3 by 2 between for the domain x belonging to 0 and 4, and then we wish to find the arc length. Begin by initializing the variable and the function. As a good practice, we could plot the function itself for the given domain. So this is how it looks like. And now we wish to calculate arc length. So to do that, we basically are integrating the square root of 1 plus dy by dx whole square over our specified domain. So if I run this, it will take a minute or so. This came up fast. Maybe the next one takes. Anyways, this gives us length of the curve for our length of this curve for the chosen domain to be around 69.5. Okay. Another example on arc length, y square is equal to 1 plus 2x whole square, and we have been told that we want to select y which is greater than 0. So my y basically becomes square root of 1 plus 2x square. If I plot y of x between the domain x belonging to 0 and 1, that's how it looks like. At x equal to 0, both y and x are y is 1, whereas at x equal to 1, y becomes root of 3. And then we calculate again the arc length by doing an integral over the square root of 1 plus dy by dx whole square. Okay, so for our chosen range, I think this is the one that takes a moment. Okay, we'll wait for a moment for this to calculate. Uh, I'll Okay. I'll stop this computation for a time being. If required, we can come back to this at the end. It's taking a bit of a time. Yeah. We'll move on to the next example. So the next example deals with finding arc length for a parametric curve this time. So x of t and y of t, with t being a parameter and t varies from 0 to pi. Both of them have a e raised to t expression, and then they are multiplied with sine of t and cos of t respectively. Again, the same process. We start off with variable t. Here we are writing x of t, so x of t basically means that x tells SageMath that x is now an expression, not the variable default variable x that SageMath assumes. Similarly, we define y of t, and if I do a parametric plot for x of t and y of t, I see this thing. So at t equal to 0, both x and at t equal to 0, e raised to t is basically 1. X is 0, but y is 1. So this is the point of t equal to 0. And at t equal to pi by 2, cos of pi by 2 would go to 0, sine of pi by 2 would become 1. So e raised to pi by 2 would look something like this. And at t equal to pi, again sine of pi would go to 0, which means x would go to 0, but y would be negative. So if I want to check what my value is, if I do e raised to pi by 2, dot n, I get 4.8. So this is around the point this curve intersects here. Just zoom into this. Okay. To calculate the length of this parametric curve, we basically do dx by ds is uh, the infinitesimal length of this curve is nothing but dx by dt uh, square root of dx by dt whole square plus dy by dt whole square. So this becomes my expression s. If I do, what that looks like is basically twice of e raised to 2t. So if I do a show, so this is how my dx by dt whole square plus dy by dt whole square looks like. We need to take square root of this and then integrate it with respect to t. Square root of this would be nothing but root 2 e raised to t. And then we are integrating it from 0 to pi. So root 2 e raised to t will be integrating from 0 to pi. This is what we obtain as our expression. Okay. So the length of the curve is fairly large. It's around 31. Next, we wish to study solid of revolution. We want to find out what its volume looks like. So it's basically the curve. It's formed by rotating the curve y is equal to cos of x bounded between 0 to pi around the axis. Sorry, when it is revolved around the axis, y equals 1. So this is how
Sir,
my
please once show the
hmm,
previous code.
yes, this one
Parametric plot.
parametric. Okay, any doubts here? Or like, have I made a mistake? this is a better way to show that. So we have been basically asked to find a volume of solid of revolution for this particular shaded area, which is bounded between y is equal to cos of x and y is equal to 1. So, so if I if I say to a revolution, I think I should have 1 minus f. Not minus 1. So my 1 minus f basically vanishes at x equal to 0, and when x goes to pi, my 1 minus f becomes 2. So this is how the 3D solid would look like. And if I now calculate its volume, it's nothing but pi times 1 minus f of x whole square. So pi times f of x minus 1 whole square for x going to between 0 and pi. Once I calculate this, I get my volume of solid of revolution to be around 14.8 units. Okay, so this is, yeah, this completes this problem. The next example that we have is we are asked to define a region R which is in the first quadrant and bounded by two curves y is equal to x square and y equals x minus 3x3. And then we have to calculate, say, the area of this region R as well as obtain the volume of a solid of revolution by rotating x about by rotating, sorry, the region R about x-axis. Again, the same process. We initialize the variable. The functions, the two functions, I have labeled them as y1 and y2. Y1 being x square and y2 being x minus 3x whole cube. So these are my function definitions. And now I want to plot p1 and p2 together for the entire range -1 to 1 and -1 to 1. Now we are interested only in the first quadrant. So we'll be looking at only this part. Another thing is we can see that y2 is so the y2 is in the red and it is above the blue part, which is y1. So we are only interested in, say, this part to this point where y2 is above y1, and this creates like a bounded area. Here basically up after this these two curves will be diverging, so we won't have like a finite value. So that is why we need to find out this point also. We do that using the solve function. So I think I already used solve. So the help basically says that you tell solve about your system of equations and which arguments you want to solve for. So I want to solve my system. My equation is basically y1 equals y2. So y1 minus y2 equaling 0 for the variable x, returned in the form of a solution dictionary. And I saved it into a variable called as PTS. You can see that there are three solutions. So you can see this from the graph itself. There are three possible solutions. One is a entirely negative solution of -1/6 root of 13 -1/6. So this is negative. This is positive 1/6 of root 13 minus 1, and the third is 0. So our curve is basically bounded between 0 and this value. So if I evaluate what those bounds are, my x coordinate bounds are basically 0 and 0.43. So 0 and 0.43. Now I'll go and plot this region again. What does this region look like? So while plotting, I'm plotting y1 as it is, but for y2, I'm filling it up to y1. So that creates the shaded area, which is our region R. So this is region R. And now I wish to evaluate its area. Again, like straightforward, you basically do y2 minus y1 integral over dx with the limits provided as a and b. So my area is basically integral of y2 from a to b minus integral of y1 from a to b. This is how at least I have coded it here. Once I run this cell, I obtain my area to be very small, about 0.04 to be precise. Okay. Next, we have been asked to plot a solid of revolution. So that is done using revolution plot 3D. I think I've already used this above. So we'll be providing it with a range and a function. So what I'm doing here is I'm plotting y1 and y2 separately as the two bounds for x going from a to b, and with two different colors. So my if I run this code, what this is how it looks like. So the red one is my y1, the cyan one is my uh, the cyan one is my y2, and the area between them creates my uh, revolution plot. And if I have to calculate, sorry, if I have to calculate the volume of this uh, cyan portion in between, so it's basically pi times y2 minus y1 whole square. So the radius at any point is nothing but y2 minus y1 and integral pi r square over our range of x, which is a and b. So once I do this, my volume of this solid of revolution turns out to be 0.14, 0.014, sorry. Yeah. So this is how this, this is how you can calculate, say, the area as well as volume. Okay. The next example that we have asks us to find the area bounded by a loop of the curve r is equal to twice of cos of 2 theta for theta varying from 0 to pi. Again, the same steps: define the variable, define the function. So I should write r of theta, and it goes from, for a given theta, it's basically 2 cos 2 theta. If I want to do a polar plot, this is how it looks like. So when theta equals 0, 2 cos 2 theta will also be 0. Sorry, 2 cos 2 theta will be 1. So my r will be 2. As theta increases to pi by 4, cos of 2 theta becomes cos of pi by 2, which becomes 0. So at theta equal to pi by 2, my pi by 4, my r equals 0. At theta equal to pi, at theta equaling pi by 2, my cos of this cos expression basically becomes -1, and my radius becomes -1. So this is my theta equals 0, theta equals pi by 4, theta equals pi by 2. Again, then this curve moves like this to go to, again, theta equals 3 pi by 4, and finally theta equaling pi. So it moves like this. This is a polar plot, and we are asked to calculate the area bounded by this loop. So as we have seen already, uh, as we have seen already, the area under in polar coordinates is basically integral over r dr d theta, varying for r as well as theta. If we integrate it with respect to r, it basically becomes half of r square d theta. So that is what we are using here. My area is nothing but integral half of r square over the variable theta for the value 0 to pi, for the limit 0 to pi, and then I calculate this numerical value, nothing but it's pi. I just do a is pi. So yeah. Okay. Next, Next that we have is basically another example, but here we are asked to calculate arc length for a polar plot. So my curve is basically r equals 1 plus twice of cos of theta, theta varying from 0 to 2 pi. Again, same steps, define the variable theta, define my radius as a function of theta, 1 plus cos of theta, 1 plus cos of theta, and then I'm doing a polar plot. This is how my polar plot looks like. Again, if you have to see how this polar plot works, you have to at theta equals 0, my r is 1. At theta equals pi by 2, sorry, at theta equals pi by 2, my r is again 1. Yeah, my r is again 1. So, sorry, at theta equals 0, my r is 3. At theta equals pi by 2, my r is again 1. At theta equals pi, my r goes to 0. At theta equals 3 pi by 2, my r becomes 1. My, sorry, it's twice of cos theta. At theta, at theta equals pi, my r becomes minus 1. So, it's going like this, flipping around, r becomes negative, then again r becomes positive. So, if I have to see it in a different way, what I could do is plot of r and then see what the values of theta looks like. So at theta equals by 2, my at theta equals pi, my r is negative. And there are some points in between where my r value becomes negative. Then again it becomes positive. So the curve goes like this as theta goes from 0 to 2 pi. To calculate arc length, we basically have to calculate dr by d theta, and once we have that, we write integral as square root of r square plus dr by d theta whole square integrated with respect to theta for the limits 0 to 2 pi. That will give us our arc length. So, my arc length looks 13.36. So the arc length of this curve ends up looking like 13.36. Okay. So far, like I think most problems have been straightforward itself, like application of all the different formula and integrals that we have seen. Now we have a few specific problems. So suppose we are interested in calculating the area of surface obtained by rotating a polar curve about the x-axis. So we have a polar curve of the form r is equal to f of theta. Theta is restricted to some interval a comma b, which is a subset of 0 comma pi. So theta will be within 0 and pi always. And then we rotate our curve about the x-axis. From that, we wish to see what surface is generated, and for that surface, we want to see how our area of the surface looks like. So the formula for the same is given here to us, that it is an integral from the limits a to b 2 pi r sine of theta into r square plus dr by d theta whole square d theta. So again the same process, initialize the variable theta, initialize the function r of theta. Next, do a polar plot, but within our limits of 0 and pi. So this is how my polar plot looks like. Theta equals 0 to theta equals pi. So this is our pi square root intersect, right? And now we wish to calculate an integral over theta. So before that, we want to calculate derivative of r with respect to theta. So dr by d theta, that is basically given by our variable r1. And so it's as expected, it is 2 theta. We next define our function, which is 2 pi r sine of theta, the square root of r square plus dr by d theta whole square, which is what this expression, this integrand looks like. So in our case, it looks like this. And now we want to calculate the area of this surface. It is nothing but integral of f, integral of this f of theta from 0 to 2 pi. So from this we can calculate how this surface looks like. Okay. Uh, so yeah, so this is what we this is our area of the surface. Next question we have is on limits. Suppose we want to calculate limit of a function, on x and y both going to the origin, and we want to see if it exists, and if it does, we want to find it. We again begin by specifying initializing our variable, writing down our function with the sign of x cube plus x square plus y square. Next, we do a 3D plot for f of xy with the limits x going from -2 to 2 and y also going from -2 to 2. So this is how the plot surface ends up looking like. So this is negative x. Yeah, now it's aligned. So positive x, negative x, positive y, negative y. So this is how the surface would look like from a top view. And to evaluate limit of this function f of x, we can use different approaches. We can approach the origin from the x-axis. We can approach it from y-axis or any other axis, so, or any other straight line passing through origin. So if we approach it along the x-axis, we basically have we basically specify a new variable t, calculate the function at y equals 0, which is f of t comma 0, and then we apply the limit t going to 0. So our function looks like this. Our limit comes out to be 0. If we follow the uh, line along the y-axis to calculate limit, again the same thing, but except x equal to 0. Now we have, sorry, except y equal to 0. Now we have x equal to 0 for the y-axis, and our function becomes f of 0 comma t. And then we limit it to t going to 0. If we approach the origin along any arbitrary straight line, say y is equal to m of x, how do we do this? We specify a new variable m, and we basically try to calculate limit of f of t comma mt with t going to 0. So this turns out to be 0. Another approach would have been to use nested limits. So first you take limit of f of x y for x equal to 0, and then do another limit for y equal to 0. So if I use a nested limits approach, I can end up with the same value. So pretty straightforward. A limit exists and it ends up being 0, and it can be seen from the graph also. If I do a contour plot, I think this would become more clearer. I do contour plot of f -2 to 2 and y going from -2 to 2. Equals false, labels equals true. So this is how they are slowly merging from like top. slowly. So slowly merges at this point. If I increase the number of contours, this might be more clearer than, suppose I increase it to 50 contours. Basically, is slowly coming down here to zero itself from every direction. Okay. Uh, okay. So that takes care of that example. Next, we want to similar problem. Now we want to evaluate limit for a different function, and we are asked to show that limit at origin for this function doesn't exist. So before we actually get into solving this, you can quickly do another check like yourself also. Suppose you input x is equal to r cos theta and y equals r sin of theta, right? You can see that my denominator becomes r square, whereas my numerator becomes r square times cos square theta minus sin square theta. Both of my r square will cancel out, and I'll basically have an expression of cos of 2 theta remaining, which basically tells me that uh, my limit will depend on theta, or my limit will depend on the angle of approach towards origin. So this is one of the ways that I evaluate things like this. You could see there is same thing happening here also. So my denominator is r square independent, and my numerator becomes r cube times some cos cube plus sin cube. And as we go to origin, we are basically inputting the limit r goes to 0. So this thing will, so the numerator will vanish. For this problem, again, we same approach, specify the variables, specify the function or the expression. Next, do a plot to get a feel of what's happening. So I've increased the number of plot points deliberately so that you can quickly see what is happening. So at first glance, it does look smooth, which is why you look at from the top. You can see something is off. It's coming, and then rapidly dropping, and then. Whereas if I look at from the other way around, it seems to be, sorry, seems to be smoother. So if I do a contour plot of the same, what do I have is contour plot of f for the limits x going from -2 to 2 and y going from -2 to 2. See that something weird is happening here. If I do, I'll just increase the number of, let's say 50, and labels set to 2. Okay, so depending on our angle of approach, you could have say a positive value or a negative value. You can see that here, right? So there are sharp negative values on one axis and sharp positive values on the x-axis. So if I approach the limit, if I calculate the limit first along x-axis, and first along y-axis, so I'm first setting x equal to 0 and then setting y equal to 0 using nested limit. My value becomes -1, which is what I'm seeing here. If I approach it along the x-axis, I set my y to be 0, and, and my value becomes +1. So my answer depends on which So my answer is no longer independent. If I approach it along any arbitrary line, y is equal to mx, my answer looks like m square minus 1 upon m square plus 1. Okay. So, right. So, basically, I do not have a single answer at the origin. Okay. So these two examples are clear, right? Contrasting scenarios. One where limit exists, one where limit does not exist. Next, we are asked to plot the surface z as a function of x comma y, and we are also asked to say plot contours and gradient vectors and see whether our gradient vector is indeed perpendicular to the tangents to the contour. Right. So we have our variable x comma y, and we define our function z of xy as x square plus 3y square into e raised to minus of x square minus y square. So because of this e raised to minus x square minus y square, z would rapidly decrease away from origin. So because in polar coordinates we know that x square plus y square is basically r square, this thing becomes e raised to minus r square. If I do a 3D plot for z, this is how it looks like. This is x minus 2, x plus 2, and this is y minus 2, y plus 2. So that's how the plot looks like. So the contour should have, say, two hills separated by a valley in between. If I do a contour plot, okay, what we expect. So you got two hills, sort of depression in between, and then away from it, things are rapidly decreasing. Right. If I suppose increase this to 5 to 5, increase the number of contours, say 20, should uh, quickly settle down away from it. So as you can see, it's very limited to the region itself that we had defined in the beginning. So I'll just go back to that contour plot. Uh, okay, so this is what we have. Next up, we want to calculate gradient of z, so which is nothing but dou z by dou x I hat and dou z by dou y j hat. So if I look at my gradient, contains two terms. One is along the I hat or x direction, another is along j hat or the y direction. Now I want to do a contour plot for z, and in that I want to also plot my vector field for the gradient of z. So we expect our vector field to be perpendicular to our contour plot, which is what we are seeing here. So it's normal to the tangent to the contour plot, and based on which direction it is. So when it's increasing, it's moving inside. When it's decreasing, the gradient seems to be moving outside, and basically vanishes at your x critical points. Okay. Another thing that I wanted to show us, suppose we choose a point, say 1 comma 1, and we want to plot the tangent surface to this tangent surface to this f of xy plot. So to do that, we basically calculate the first derivative of the function which is z with respect to x at the given point a comma b, and first derivative of the function with respect to y again at the given point. This will give us expression for the tangent plane, which is nothing but function value plus first derivative into x minus a plus first derivative with respect to y into y minus a. So my my expression ends up looking like this. Next, I'm looking at the gradient of z at the given at my given point. So this basically calculates my gradient of uh, function with respect, sorry, gradient of z at my given point a comma b. So these are the two components. I think I should write it like this. So these are the two components of my gradient. And now I want to plot my surface, which is z, plot the point a comma b, which is a comma b comma the z coordinate at ab. Then plot the tangent surface, which is given by the expression t of xy for x around a and b. Next, I also want to calculate normal to that surface, that is calculated by uh, that is basically calculated as a line moving from AB and Z of AB to coordinates A1, B1, Z1. A1, B1, Z1 are defined using these gradient values that we calculated here. So we basically obtain the unit normal from this gradient, which is gradient of x upon square root of gradient of x square plus gradient of y square plus 1 square. This one basically coming from when we rewrite the expression of z of xy as an implicit function. So you have z is equal to f of xy, then I can write my implicit function as f of xy minus z equals 0. And then if I take the gradients, they are basically gradient of x, gradient of y, and minus 1. These three have to be scaled into unit vectors, which is why I'm dividing everything by square root of gradient x square plus gradient y square plus this minus 1 square. So with this in mind, we get an approximate. We basically get another point lying on the normal, and I'll simply be connecting these two points using a black line. If I plot, this is how the plot ends up looking like. So I've got my surface, which is blue. I've got my point, which is red. I've got my tangent plane. So you can see that this plane is basically tangent to the surface at the given point, and then we have normal. So that if I look at it at a, say like an angle like this, you can see that this black line is, at least from to the naked eye, looks perpendicular to the tangent surface. So this creates my normal. So this is basically all the information that you would normally need for a point, tangent, and the normal. Okay, lot of things happening here. Hope this is clear. Okay, the next example that we have is we have been given a function e of xyz equaling 1 over square root of x square plus y square plus z square, and we are asked whether it satisfies the Laplace equation grad square u equal to 0, which for 3D coordinates becomes uxx plus uyy plus uzz equals 0. This basically being denoting the partial derivative, second order partial derivative. So same approach, begin by initializing the variable, then the function. We have defined our variable and function correctly. Next, we want to differentiate u with respect to x twice. So I'm doing u dot differentiation x, and then again doing a differentiation with respect to x. U dot differentiation y again with respect to y, and similarly I'm defining u z as dou square u by dou z square. If I show all these three, I get expressions which look similar but are in a cyclic order. So the x partial derivative is second partial derivative looks like this. This is the y1 and this is the z1. Now, to see if this satisfies our equation, I have to sum these three. So this is what the expression looks like. We can simplify it ourselves also. You can quickly see that there is a raised to 5 by 2 here. If I bring these three terms together, I have a numerator which contains x square plus y square plus z square. So those will cancel out with this 5 by 2 power here to make this, to make the denominator's power as 3 by 2. That should vanish out with this. But in SageMath, to do so, we will be using this command called as simplify full. You haven't seen this before, we can go through the help, which basically tells us that it will simplify whether it's a trigonometric function or a binomial function and so on. For our case, we'll be running this and the answer turns out to be 0. So indeed, dou square u by dou x square plus dou square u by dou y square plus dou square u by dou z square equals 0. So this form of u of xyz is a potential solution for the Laplace equation. You could say add a constant to it and everything would be still fine. Or you could even add, say, some function of xy. Say, suppose if I add xy, again my uxx, uyy, uzz will remain unchanged. So okay, this could also work as a potential solution. Okay, yeah. So the next problem that we have is we want to plot. We have been asked to plot a surface for z of xy, so x square plus xy plus 3y square along with tangent plane at a given point. Again, same process. Specify the variables. Specify your function, which is z of xy. Check if it's if you have given it correctly. This is, and you next specify your point and your partial derivatives and write down the equation for your tangent plane. So I could also do this show of zx comma zy. So my first, so my partial derivative dou z by dou x at this point is basically 3 and dou z by dou y at this point is 5. Once I sub this all in, uh, this is what I'm seeing as my equation of the tangent plane. Next, I'll go through the same process again. Uh, ca- Calculate the gradient of z at our point a comma b and specify that as grx and gry, gradient x, gradient y. So this is how my gradient looks like. And okay, so with this in mind, this is better. Otherwise, it would seem like 36. Next, we plot our surface z of xy between -1 to 1, little on either side. So the point that we are asked to plot is 1, 1, 5. So x and y have to be 1 and 1. So I'm plotting between -1.1 to 1.1. Then I'm also plotting my point using the point 3D expression, which takes a comma b comma z of a comma b. This will create a red point. Next, I'm plotting my tangent using plot 3D for the expression t of xy between for x around a and y around b. And finally, I'm also plotting my normal. Again, the same code as above. The normal will create a line, black line. This is what our output looks like. Okay. So a lot is happening here. My green one is my so blue is my surface, green is my tangent plane. If I zoom into it, red is my point. This is what my normal looks like. Again, from eye test, you can see that the normal does seem perpendicular to the tangent plane, which is expected, and this is how everything looks like. Okay, so if I if I have to change it to say a different point, say point two, point two, tangent plane would look like this, my point as well as my normal. Okay, so again a straightforward example I believe. Next we move to the next problem. So here we have been given from z of xy to be x square y plus 3x y square 3x y raised to 4 with x being sine of 2t and y being cos of t, and then we are asked to calculate dz by dt. So this is what we have. We first specify our variables as t of xy, variables as t and xy. Sorry, variables are only x of variable is only our parametric variable, which is x of t and y of t, and my z is basically 3x raised to 4 plus uh, 3x into y raised to 4 plus x square y. If I do z dot full simplify, I think I have to define everything as variables itself. Right, so let us z dot full simplify. It gets me a different expression, but what I basically have is a function z of t, and I can directly, because x and y were given, I can directly substitute it here and directly use that to calculate derivative of z with respect to t. This is how it looks like. And if I just want to calculate at t equals 0, right? So straightforward, t equals 0 will basically cancel out all the last three terms because they contain sine of t or sine of 2t. Only the first term remains unarmed. So 6 into 1 into 1. Okay. Next example that we have is one on the concept of directional derivatives. Directional derivatives. So we have f of xy defined as x square y cube minus 4y for a point 2 comma minus 1, and we want to evaluate directional derivative at this point in the direction 2 comma minus 1. So again we start specifying our variable and defining our function. Next we look at the limits of the we look at our point, which is a is equal to 2 and b is minus 1. I evaluate the function itself. So the function vanishes at this point. If I look at the gradient at f of x, this is how my gradient looks like. Now, if I wish to calculate the unit vector along this direction 2 comma minus 5, it will have the components dx and dy, and it is basically 2 upon square root of 2 square plus 5 square and minus 5 upon square root of 2 square plus 5 square. So this is how those the unit vector looks like. If I now calculate my gradient at for my gradient at x equals a and y equals b, it's basically minus 4 comma 8. And we know that then the directional derivative is basically dot product of gradient to the unit vector at the given point. So that is what I am doing, dx into uh, x component of the gradient and dy into y component of the gradient. So if I do this, directional derivative is estimated to be minus 8.9. Right. And if another way to calculate directional derivatives using the defining a variable a and then doing f of a plus h dx comma b plus h dy minus f of a comma b upon h, which is basically the definition of a derivative, and take its limit for h equals 0, calculate the numerical value. Again, the same thing as we calculated above. So both are two ways to do it. I think, I guess you already know all this, but just wanted to compare the two values. Next is a slightly involved problem. We have been asked to calculate temperature field at a point in 3D space. Sorry, we have been given that the temperature field at a point in 3D space is like this. Here x, y, z is 150 into e raised to minus x square minus 2y square minus 5z square. We have been asked to calculate rate of change of temperature at a point t 2 minus 1 2 in the direction 1 minus 1 1. We have been also asked to find the direction in which this temperature increases maximum and to find the value, find out that whatever the maximum value is. Okay, so we have a scalar 3D field based on variables xyz. We define that by specifying our variables xyz and the function t of xyz being 150 into e raised to minus x square minus 2y square and so on. Straight away, you can observe that as our point goes far away from the origin, x, y, and z will rapidly decrease. And this whole expression will be brought down to low values very quickly. Our specified point is 2 minus 1, 2. So this is my specified point, and my specified direction is 1 minus 1, 1. My specified direction. Right. We have to, the direction needs to be unit vector, so we are basically dividing it by square root of 3. So 1 square plus 1 square plus 1 square, 3. Right. So far, so good. To evaluate directional derivative, we'll be using the method that we just saw above. Take the temperature at ABC and take the temperature at a point which is at a distance h from ABC along the direction, along the specified direction which has components of unit vector as dx dy dz. Divide the whole thing, divide the difference by h, take the limit as uh, the distance h goes to 0. Right. So if we do this, my directional derivative comes out to be quite a small value. Now, I want to see where in which direction is the temperature increase maximum. So we know that another way to calculate directional derivative is to calculate the gradient at the given point, so that and multiply it, or rather take its dot product with the unit vector in the specified direction. In our case, this is basically we first calculate gradient of t as an expression, and then we calculate gradient of t at our given point ABC. So this is how like, this should be gradient of t. This is, that we is being carried forwarded from one of the previous calculations. So this is how my gradient expression looks like, and the second thing below is my gradient expression evaluated at the point ABC. Now now we know that the dot product between a vector and since we are interested in calculating directional derivative, we have to take dot product with respect to this vector that we have at this gradient vector that we have at our point P. The dot product between any random vector and this vector will be maximum only if that vector aligns with uh, this gradient vector, provided that like with the restriction that our vector is unit vector. So with that in mind, our basically our maximum increase in temperature field will happen if we follow the direction of gradient itself. This is also a principle that is used in optimization. So any one of you if later take on some optimization courses, or even if like if you study uh, if you do have to wish to study say like machine learning, in that also will be using gradient descent. So this principle is basically being used here, and we calculate that direction to be along grad TP 0, 1 and 2 respectively. We have to first scale it down to our unit vector, but once that is done, this is what we obtain. So this is how the direction, this is how our vector looks like. So this direction at this gradient, so the maximum rate of increase is the dot product of these two. So the maximum rate of increase in temperature at the point P is 1.59 e raised to minus. It's a very not e raised to minus into 10 raised to minus z. So this is a very small increase, but this is the maximum increase that we can get at our point. If you, suppose we were to look at a point which was much closer, right? So 0.1, you might see larger values. You can already see that the gradient values have jumped, and you have a relatively larger increase in temperature. Okay, so this completes this problem. Next problem is on critical points, basically local minima, maxima, saddle points for a function of the form f of x y is twice of x square minus y square minus x raised to 4 plus y raised to 4. Same process, begin by initializing variables, defining the function. Next, a good idea if you can is to plot the function to get a feel of the problem. This is how it looks like. So it seems like there are depressions, and perpendicular to those depressions there are so there are crests and there are troughs which are perpendicular to each other, and then after some point this whole thing is seems to be increasing very rapidly. If I look at it from the point of view of a contour plot, so this is what my contour plot seems to say. So there are crisscross lines for x equals to 0, then they increase after a point, they increase very rapidly, and there are some negative points also here. So minus 60, minus 120, and so on. Okay, so we will be calculating partial derivatives of f of xy with respect to x with respect to y, and then the second partial derivatives. So I think this is quite straightforward. Then we define critical points as the solution where the first derivative of f of x and the first derivative of f of xy with respect to y, both of them vanish. We wish to calculate solutions for both x and y and store that into the CPTS, the critical points array. Critical points array. So this is what we see. There seem to be like a lot of points. We'll be using the extremum function that we already looked at in class. A brief recap of the same is as follows. We calculate the second derivative with respect to x, y, and the mixed derivative at the given point, and then calculate. This basically becomes our Hessian, and we calculate determinant of the same. And if the determinant is positive, and the sign of the first term is positive, you basically have a local minimum. If the determinant is positive but the sign of first term is negative, then you have like a local maxima. If the determinant is negative, you have a saddle point. So this is what we have. If I basically run this function, and now I calculate. I again specify my variables x and y, write down my data array which contains critical points, type, and values, and then value, and then I solve for all the critical points, first derivative of x with respect to x and with respect to y both being vanishing, and then provided that my solution x and y coordinates are real, I append them to my data along with the value of function that I obtain, as well as whatever this extreme function returns. With this in mind, I run this for loop and I obtain a table. It looks like this. So you have few critical points. Total of, I think there are 9 critical points, 0, 1, minus 1, and 0, 1, minus 1, respectively for x and y. And this gives us the value for all the points. And you can see that there are 2 local maxima, 2 local minima, and 5 saddle points. If I go back to my plot, what I'm seeing is, so if I go back, what I'm seeing is these are my 2 local maxima, these are my 2 local minima, and these 5, like 4 corners of that square and center of the square are my saddle point. If I look at it from this function plot, from this 3D function plot, I restrict the, this is what it looks like. So what I'm saying is these 2 are my maxima, these 2 are my minima, and here I have 4 saddle points at the corners as well as at the origin. Okay, so this is also done. Next up, we have a problem where we wish to find a point on the plane defined by 3x plus y minus 2z equal to 16, and we want to find the point which is closest to the origin. So there are different ways you could do this, but I wanted to try to solve this in the form of like a local minima or like a local minima problem. So I define my variables x, y, and z. I define my function x, y, and z, and then uh, so which is my equation of the plane, and then I do an implicit plot. What do I see in this implicit plot is basically this is my z equals 0, so I need a few more points here. So maybe x going to minus 10, going to 10, or I'll leave it like this for the moment. So this is my z equals 0. I also need to find where my y equals 0. My y equal to 0 lies on this point. So z equal to 0, y equal to 0. And similarly, my x equals 0 lies here. So my xy and my z equal to 0. So somewhere here I have an origin point. And now what I am doing is I am creating a new scalar field z of xy is equal to basically the same equation for the plane, but it has now been flipped around to make z a function of x and y. So it basically is half of 3x plus y minus 16 Then I'm defining a different function called as the radial distance function, which is nothing but the Euclidean distance between my point xyz and origin, which is x square plus y square plus z square. Right. So this is how my function f looks like for x and y. Now if I want to see where my I can see if I want to see this, what I could do is I could do a plot function. So plot of plot 3D of f and x going from minus 10 to 10 and y going from minus 10 to 10. So this is my function. So you can see that there is clearly a minimum somewhere here. So there is a point where the radial distance is minimum from xyz to origin, and apart from that, this function seems to be like convex. So it seems like it only has one minimum, which is also what we expect for the plane. For the plane to only have one nearest point. Again, same process. Define the partial derivatives of the distance function with respect to x, with respect to y, as well as second derivatives. Calculate the critical points. So there is only one critical point. Just to be safe, we run it again through the loop that we have defined above, wherein we also calculate what the type and uh, value at the critical point is. And once I run this as the table, what I see is that at 24 by 7 at 8 comma 7, I have a local minima, and the distance square of the distance is 18.28. So somewhere around 4.3, 4.2, 4.3, we have our distance to the origin. Right now I'm plotting the function surface, and let's see what all we have plotted. So first we have a blue plot for Z. So this is my blue plot for Z of xy. So blue is my plane. Next I have a green plot for Z equals 0. So my green plot it as Z equal to 0, and my x and y are between 0 and 5. I am also plotting a black spot, black point, which is basically at 0, 0, 0. So this is the origin. So my plane, my xy plane or z equal to 0, my point of origin, and this is my closest point. Critical point 0x, critical point 0y, and z evaluated on the plane. Okay, so this is how this is how this thing looks like. If I take any other point on the plane, it may not seem so, but it will be always farther than this point when referenced against origin. Okay, so these are all the questions that I have for today. Anyone has any specific doubts?
Sir, please show the critical point code.
Critical point. You mean the extreme function or
No, no, last solve critical point.
last one? No. So the solve
Just,
function.
just wait.
Yes. I think I'll be uploading this all on the drive folder. You guys have access to the drive folder, right? Okay. Is this all right? Do you have any doubts here? Any other doubts? So a lot of problems for today, but I felt like the content was too wide covered in this week. In the upcoming week, we have less code and more technical concepts, so that might have lesser number of examples. Let's see how that goes. Okay, yeah, thanks. Then, if you have any doubts, you can ask them. Otherwise, we'll call it a day.